Hello, my name is Álvaro and I am a PhD student at the University of Colorado Boulder. In this paper, Professor Rada, Professor Schob, and I are going to introduce our new numerical simulation framework that we have designed to study the growth and detachment of axisymmetric bubbles in microgravity when subject to inhomogeneous magnetic fields. First of all, we want to explain why we are interested in this fundamental fluid mechanics problem. In order to do so, I want to tell you that we are really interested in the dynamics of liquids and particularly multi-phase flows in microgravity in the context of electrolysis and boiling technologies. So you know perfectly that due to the absence of gravity, when you have a nucleation surface like an electrode or a boiling surface, the bubbles start generating in that surface and start accumulating. And if you don't implement countermeasures, what it happens in the end is that you have this layer of foam, of bubbles, that is hard to detach, that reduces the efficiency of our system, and also that has to be separated in a later stage. Indeed, from a technical perspective, these separation states require significant mass and power penalties. As you can see, for instance, in the schematic diagram of the oxygen generation assembly of the International Space Station, where you have a series of pumps and sensors and controllers that account for a significant mass penalty of the system, and that, if possible, if there was a way to remove them, it would be nice to get rid of them. So in order to perform phase separation in microgravity, there are a few technologies which are really common nowadays. One of them is using membranes, which are passive, that is, they do not require power, but they also have a limited lifetime and are not completely reliable. We can also employ rotary devices like centrifuges that employ an inertial a centripetal acceleration to separate the phases. Or we can even spin our spacecraft as proposed by Doyle and Peck for a CubeSat project, just to perform the separation. Recently, some researchers have proposed also to employ the natural dynamics of bubbles that tend to expand towards the minimum energy configuration, which is spherical. As I said, some researchers have proposed to employ conduit geometries to employ this expansion to separate the phases. So this is what we have. None of these approaches is perfect. All they require have complications and have operational environments for which they are appropriate and others for which they are not. So in order to complement or substitute these approaches, we came up with the idea of using magnetic fields to induce a gravity equivalent buoyancy force in space. So the idea is actually very intuitive. If you have a high density magnet and a multi-phase flow, the different elements of the different components of the multi-phase flow will have different magnetic susceptibilities. That is, they will feel attracted or repelled from the magnet at different rates. And in this way, we can generate a buoyancy force. In the case of diamagnetic liquids tend to be repelled from the magnet. So the gas bubbles feel attracted towards the magnet. And we can employ this, for instance, to remove material from the surface of the electrodes and electrodes or boiling surfaces and enhance their efficiency. In the case of the para or ferromagnetic liquid, carrier liquid, what happens is that the magnetic force attracts the liquid and repels the bubbles. But these are the two sides of the same coin. The constant is exactly the same. The only thing that you change is a sign in the equations. You can employ this concept over the surface of your nucleation element, or you can employ it as a standalone device that separates the phases. And this concept has been explored in the past in previous parabolic flight experiments. Or you could even combine this approach with other phase separation technologies, like the recent conduit geometry proposal that I had just mentioned in the previous slide. By the way, all this discussion of this new magnetic electrolysis and phase separation concept can be found in this paper that is currently under review at the Journal of Spacecraft and Rocket. One thing to note is that this magnetic force is not the Lorentz force. It is a diamagnetic force that depends on the intensity of the magnetic field and on the gradient of the magnetic field. So the question that we ask ourselves from very fundamental perspective is, okay, so we have a bubble that is being created at the surface of an electrode, and this bubble is growing. And so we wonder what is the departure diameter or volume of such bubble under the influence of the highly inhomogeneous magnetic field in microgravity. What is the shape of the interface that is important for the design, and also which are the natural oscillation frequencies of the bubble. Because if we know the natural oscillation frequencies, we can implement some sort of piezoelectric device or even an oscillating magnetic field that excites those molds and detaches the bubbles more easily. So in order to answer these questions, I'm going to cover several approaches that we can take. One of them, the most obvious, is the purely analytical approach that is based on the momentum balance in the surface of the bubble. So you input all your contribution, surface tension, in residual inertial acceleration, magnetic force, etc. And you propagate this equation, and you basically compute the interface thanks to this balance. Up to a point where the balance cannot be accomplished, that is, the surface becomes unstable, and the detachment is produced. Such detachment can be modeled and has been modeled extensively in pool boiling research by using the Fritz equation that we extended to the magnetic case by assuming a constant magnetic force in the previous paper that I mentioned. The displacement is very easy to model and to study pretty reliably by means of the terminal velocity, which is no more than the steady state velocity that happens when you compensate the external forces with drag. This approach can be found in many papers and many works, and also on electrohydrodynamics in space. So it is pretty popular. Another, an extension of this approach is also the famous, this is a book that I like a lot, Low Gravity Fluid Mechanics by Miskis and co-workers. I said famous because this is a fundamental work of low gravity fluid mechanics, and here you can find many interesting results that we can use for this sort of problems. And I wanted to devote a slide to this book because the authors were smart enough to generalize the results for any potential. It turns out that the magnetic force derives from a potential for an isothermal flow, which means that you can use all these 70s results in the magnetic bubble detachment problem by simply substituting the force potential. For instance, you can determine the meniscus profile in this manner, or the stability properties of your surface, or the free surface oscillation frequencies. However, I must say here something important. All these results and equations work very well from the numerical perspective and also from the analytical perspective when the potential depends on just one coordinate. Like, for instance, you have a gravity potential, it just depends on the direction of gravity. But if you have a highly homogeneous potential, like the magnetic force, diamagnetic force 1, these equations are much harder to solve numerically, and they rarely have an analytical solution. So the problem becomes much more complicated. You can also employ purely numerical methods. For instance, Marchette and co-workers have implemented magnetic source terms in the momentum balance equations in ANSYS Fluent to model the reorientation of liquid oxygen in microgravity, or to model the retention of liquid oxygen in accelerated environments by means of surface evolver, and an additional energy term in the energy equation has to be minimized by gradient descent. So these are just some approaches. I'm pretty sure there are more ways that have been proposed in the past, but basically this covers the main techniques that have been around for years to study the influence of magnetic fields and electric fields in low gravity. So the question that you may be asking now is, why are these techniques not enough? And in order to answer it, I will come back to the governing equations of the system. So first of all, you have the Navier-Stokes equations. Here, mass and momentum balances. The momentum balance depends on this term, the source term, which is basically the divergence of the mass square stress tensor that gives you a volume force. And this mass square stress tensor, for the case that we are considering, including magnetic fields, viscosity, and pressure, is composed of these three terms. Now, these terms of the mass square stress tensor depend on the magnetic configuration of your system. And in order to determine such magnetic configuration, you need to solve Maxwell equations for static magnetic fields, that is, the divergence of the magnetic flux density and the rotational of the magnetic field has to be zero, plus the appropriate boundary conditions. So you can see very clearly something here. These are not independent problems, these are coupled problems. So if you have a magnetically susceptible liquid, such as a ferrofluid, you cannot easily decouple these two systems without incurring in significant errors. The only way you can decouple both systems is when you have low susceptibility liquids, such as water or liquid oxygen, which are para or diamagnetics. Only in that case you can decouple both problems. But be careful, because as I said, even if you decouple both problems, the analytical and numerical approaches are complicated because of the presence of a highly homogeneous magnetic field. Indeed, just to reinforce this idea that the magnetic field is so inhomogeneous, I want to show you some results from the magnetically enhanced electrolysis and phase separation paper that I mentioned before. So you have, for instance, in a space that is in microgravity conditions, a 1 millimeter diameter oxygen bubble in the ionized water at standard conditions, and you place it in the vicinity of a high density magnet with a maximum residual magnetic flux density of basically 1.5 Tesla, which is the maximum you can find nowadays in the market. You will see that the terminal velocity of the bubble grows from 0.1 millimeters per second at approximately 2 centimeters from the magnet up to 10 millimeters per second. So this is a huge increase in a very small distance, which means that the magnetic force is varying very fast. In other words, that the magnetic force is highly homogeneous in your system. So this is something that you have to take into account, because this decay is something that numerical systems usually don't like, and particularly numerical solvers for analytical equations. So also you have to consider that the force that we are dealing with here, in the case of water, is of the order of 1 nanonewton per millimeter cube. This is a very small force, but in the absence of other interactions, it is very significant. If instead of water or a low susceptibility liquid, you have a ferrofluid, like in this work by Yamasaki, where they pumped a small bubble into a ferrofluid while subjecting the system to the magnetic field generated by a coil, then the things become much more complicated, because ferrofluids alter the magnetic field of the system. And also because this bubble will be subject to a highly homogeneous contour boundary conditions. So in this case, even though the magnetic force was directed in the same direction as gravity, that is the buoyancy force, the magnetic buoyancy force exerted on the system goes up in the same way as normal gravity conditions. And even though you can see here that the magnetic flux density has a relatively small influence in the volume of the detached bubble, even in this case, by just using dynamic balances without considering all the complexity of the problem, you get at least a 17% error. As you can imagine, in microgravity conditions, when the masking effect of gravity is removed, this error can be expected to be much larger. So you need a specific simulation frameworks for this. And this is exactly what we are presenting in this work. So I want to introduce this. Basically, you want to study capillary flows in a space, in microgravity, or in any other application on Earth. You can basically employ an interface tracking approach, which is what we use, or an interface capture approach, like, for instance, volume of fluid. The problem of the second is that it is subject to significant numerical diffusion problems in the interface of the liquid. And since we are analyzing just an axisymmetric bubble and not a very complex multi-phase flow, the interface tracking approach is optimal. Indeed, the codes and the approaches that we have implemented in this model have been tested extensively in other problems, for instance, in the stability of liquid bridges in microgravity at the International Space Station. And we have obtained, particularly Professor Rada has obtained very accurate estimations of all the parameters of the system. So we rely a lot on this numerical framework. We believe that they will give physically accurate results for our problems, as it has given in other coupled fluid magnetic problems in the past, for instance, when studying magnetic liquid sloshing in some of my previous works. So in this simplified first model that we are considering, we have a gas bubble submerged inside a magnetic liquid, like a ferrofluid, and subject to the magnetic field generated by a magnet, which is placed in region E. Region C and D are just implemented to satisfy the boundary conditions of the magnetic problem. So these are 5 regions with non-singular mappings. That is, we map everything into a rectangular domain that we then solve numerically by means of the Chebyshev spectral collocation method. And we then solve our system in a monolithic manner. That is, all the equations are solved together. We employ a full implicit Newton-Raphson approach that is able to give us the steady state solution of our problem in a single iteration step or time step, for which we use second order finite differences. And the outcomes of this approach are, first of all, the shape of the interface of the bubble in any conditions, magnetic fluid conditions that we want, the departure volume that is related to the loss of stability, the stability properties and natural oscillations of the bubbles, and also, and this is very interesting for those dynamic approaches that I mentioned before, the nonlinear time-dependent simulation. So if we want to model what a dynamic force makes in the bubble or produces in the bubble, this is an optimum simulation framework to do so. I don't like, I will be very honest with you, I don't like to place equations in my slides because people lose attention. But since we don't have a proceedings paper to deliver in Cospar, I just thought that someone might be interested on this. So very briefly, we implemented Navier-Stokes equations employing an axisymmetric reference system. And the only thing to notice here is that the momentum balances in radial and vertical directions both implement this magnetic force that depends on the gradient of the magnetic field and on the magnetic field itself through the magnetization vector. Regarding the static Maxwell equations, we have to solve the previous system on which we remove the current terms because at least at this point we are not considering coils. And we express, in virtue of Helmholtz's theorem, we express the magnetic fields as a function of a scalar and a vectorial potential. And by doing so, we get to these expressions in an axisymmetric cylindrical reference system. And the only thing we have to take into account is that for the domain B that contains the ferrofluid or the magnetic liquid in general, we need to add the constitutive relation of the liquid that is given by this expression in the second term of this divergence of H equation. And the constitutive relation basically defines the magnetic properties of your liquid, while for ferrofluids, it influences these 4 parameters here. For liquid oxygen, for instance, it only affects this E parameter that defines the magnetic susceptibility. Regarding the boundary conditions, they are just the common ones that you can find in this sort of problems: non-penetration in the wall and asymmetry in the axis. With maybe the particularity that in the interface balance you have this pressure term, magnetic pressure term, that is usually forgotten by other authors. But that may be important for highly susceptible magnetic liquids. And regarding the magnetic problem, we just have to point out that we implement a magnetic isolation condition in the external contours of the problem, which forces us to consider a very large simulation domain. So this is physically reliable. In order to study the oscillation frequencies, modes, and stability, we assume a time dependence. I mean, once we have the steady state solution, we assume a time dependence of the different variables of the problem of this form. And then we compute the eigenmodes and eigenfrequencies from this generalized boundary value problem, where the J is the Jacobian of the full system, and the Q implements the time-dependent terms. From this, we get oscillation frequencies and also the damping ratios of our system, and finally, the stability properties for different volumes. I cannot give you more details, but if you want further explanations about these equations and about the numerical approach, please refer to these 2 papers, published one of them last year and the other in 2016, regarding the numerical approach. So, in conclusion, the dynamics of pin magnetic bubbles remain largely unexplored in microgravity. The coupled magnetodynamic problem that we had just described requires dedicated simulation frameworks, in particular when you employ highly susceptible magnetic liquids. And we have been able to come up with this framework, which is physically accurate, efficient, and flexible, and that enables us an unprecedented level of analysis with respect to previous works, and also gives us the possibility of future technical developments. Because this problem allows us to compute the steady-state solution of our axisymmetric bubble, the oscillation frequencies and stability properties, and also the nonlinear time-dependent evolution. So that was all from our side. I would like to thank you for your attention. And please, if you have any questions about this or any suggestions or comments, please feel free to reach out to any of these links or websites. Again, thank you very much.